Hi, everybody. You're going to really love this interview with a man who's been a mentor to me, whether he likes it or not, since I was a wee lad, and that's Dr. John Mather of National Aeronautics and Space Administration, who has been a foundational leader in the field of the cosmic microwave background radiation, and now he studies the early universe in a slightly later garb via the James Webb Space Telescope, which he is one of the lead scientists on and foremost proponents thereof. John, of course, won the Nobel Prize in 2006 and features prominently in my book, Losing the Nobel Prize. He is a hero to many of us. He's an old-fashioned experimentalist, and he is an amazing spirit in terms of all the great things he's contributed with humility and just a tremendous individual. I learned so much from him. To get his answers to the thrilling 3 final questions that I've patented and trademarked and copyrighted and all those. No, I didn't do that. But I want you to sign up for my mailing list at briankeating.com, and you'll get access to those answers, and you won't want to miss them because his answers really portray a very gentle soul, a kind of Zen-like character who I got to know so much better on this interview. And you won't want to miss the way that he responds to the questions that I use to humanize these ultra brainiacs, these laureates who honor me by coming on my show, as well as all the guests that do so, I have to be honest with you. So please subscribe to the podcast, wherever you're getting this, listening to this, watching this. Give it a thumbs up, and also subscribe to the mailing list if you want to get John's answers to the thrilling 3 final questions. John's the 9th Nobel Prize winner I've had on the show, and he's really one of the best. So sit back, enjoy this episode of Into the Impossible with Dr. John Mather.
Any sufficiently advanced technology is indistinguishable from magic.
And we are talking with John Mather, who has been a hero of mine for decades. I met him when I was a young graduate student, right after his most noteworthy discoveries in COBE and the FIRUS instrument and the real motivation, along with a huge team. And I want to talk about scientific leadership and team building and all the things that you're known for that are so hard to learn, much harder than learning about the cosmic background radiation, I think. But John, how are you doing today?
I'm fine, thank you. I'm surviving this COVID thing pretty well. Pretty well set up at the house here. I don't have to go out. We get groceries delivered, so we're taking advantage of modern technology to protect ourselves and to travel the world virtually. That's what we're doing all the time.
Yeah, it's certainly, if someone had told me a couple of, months before this all started that we'd all be kind of cooped up and communicating only via telecom, I would have said, welcome to my world, because I always thought, John, that astronomers like us would spend our time on telescopes, not on telecons. But unfortunately, we seem to spend most of our time dealing with these. And but surprisingly, people have made it through. And I've done it in concert to maintain my sanity by talking to many people on this show, on the Into the Impossible podcast. And many of them are your fellow Nobel laureates. And I want to send greetings from some of them to you, like Ray Weiss, Barry Barish, and others who have honored me by coming on the Into the Impossible podcast. So this will be on YouTube, and you'll see their videos there as well. I want to start off with your history, because I've been going over some of your backstory, your origin story. And I always think it's interesting. People are fascinated with origins, either their own origins, their birthdays, and New Year's and things like that. What attracted you most about cosmology since it became your career? But did something about cosmology and wanting to understand the universe first lead you to this career, or was it merely something you were good at?
It's much more accidental than that. When I was a kid, I was reading books about cosmology. There was 1, 2, 3 Infinity from George Gamow, right? Yeah. And so I was aware of the expanding universe story, but I thought, well, we'll never be able to figure that out, will we? And then in college, the cosmic microwave background was discovered while I was a freshman, I think. And so, okay, well, maybe people could learn a little bit. Then I'm in graduate school, and I think I want to be like Richard Feynman. I want to figure out the secrets of quantum mechanics. And people said, well, by the way, are you rich? Because there are no jobs for theoretical physicists right now. So, okay, no, I'm not. So what else would you like to do? Okay, I'm beginning to get tired of studying in the library, so I'll go around and talk to faculty members, see what they're doing. So I talked to a couple, and this project of measuring the cosmic microwave background was up. It was just 5 years after the discovery. Oh, this is something a graduate student could make progress on. So I worked with Mike Werner, who you know well as well, my counterpart on the Spitzer Space Telescope.
That's right.
Anyway, so we worked together in Paul Richards' lab, and we built up some stuff, and we measured some things, and well, it worked, but it wasn't very interesting. So, okay, well, this is pretty hard. So then my thesis advisor, Paul Richards, went on a sabbatical, and he came back from Britain with a concept for a balloon-borne instrument that could measure the spectrum of the cosmic microwave background radiation, and it could do it a lot better than we could ever do it on the ground. So, okay, so I'll work on that. So we worked on that for a while, and finally we got tired of working on it and fixing it. We said, well, it's time to go try it. So we took it down to Texas to the balloon base there, and we launched it, and it didn't work. Oh, crap. Excuse me. So now what do we do? Well, Paul let me finish my thesis describing the non-working flight hardware and the not very interesting ground-based experiment. And I was off to New York to get a job at NASA. So, okay, well, I'll do something else. This is way too hard. So I got to New York. I was working for Pat Thaddeus, and we were going to do molecular astronomy with radio telescopes. Well, of course, it turns out that's also really hard. So, okay, but after I've been there about 6 months, NASA said, oh, well, it's now 5 years since the moon landing. What are we going to do now? We'll ask the scientists what they want to do. So we got a call for proposals, and I said, boss, my thesis project failed. We should try it in outer space. Okay.
Scaling up, they call that, literally.
Yeah. So I thought, well, this isn't going to work, but we might as well try. So we wrote our little proposal, and nothing much happened for a while, but it was clearly interesting to some people. So a couple of years later, NASA said, yeah, well, this is a serious idea. We're going to start up a study at NASA Goddard Space Flight Center in Greenbelt, Maryland, where I still am. And so they said, here, let's give you some good engineers to work with. And so it's not just an idea, it's let's figure it out. Let's make this happen. So that was 1976. And a lot happened between then and launch, but it did work. So launch was in 1989, and right away we got our first results. The ones that are famous. So within a few weeks, we had a spectrum of the cosmic background radiation that was, so much better than anything we ever could have done another way. Being in space is good. And so I got a standing ovation when I showed my chart to the Astronomical Society. And oh my golly, I guess this is really important. My perspective had been, well, my job is just to get it right. I wasn't even thinking about whether it was important, just got to get it right. So I was really pleased, but a little surprised by all that enthusiasm, because I thought, doesn't everybody know that's the right answer? But no, we don't, of course.
Right. That's why we call it science, right?
So that's how I got started. And a couple of years later, another instrument team on our mission made the front pages with the map of the cosmic background radiation with the hot and cold spots everywhere. And that was the first clear discovery of that. And so suddenly now we have a measurement of the initial conditions of the universe, the spatial structure and the temperature. So, okay, you ought to be able to figure out everything if you know that. Well, not quite, but you should try at any rate. So I was stunned by that one in a different way. I thought, well, this is way too complex. My theoretical friends are never going to figure this one out. But actually they did pretty quickly. They settled on the equations that should describe this process. And they were able to make a very good model that explained everything we saw. And then when we got more data from more experiments and 2 more satellites after that, it all fit beautifully. Up until very recently, when, as everybody knows, we're having a problem again, that we got 2 different measurements of the Hubble constant, and they're significantly different. So I don't know where that one's going to go, but whoever said nature was simple
So many things to unpack that you said that really harken back to lessons that I've learned and try to teach to my students, channeling your advisor, Paul Richards, who is, of course, a friend and a colleague on the Polar Bear and Simon's Array projects, co-led out of UC Berkeley, your alma mater, with by Adrian Lee, who's one of my oldest friends, and we've been working in this field for 20 years plus. And some things that, as you're talking, I'm just wondering, like, you and I share a little bit of the DNA of Paul Richards, in that I'm sure you say things, every so often that come directly from him, such as when he, would just stand up during a talk and say, "You're not telling a fiction story, you're telling a scientific story." So get to the. Do you have any anecdotes from Paul that that are rated G for my audience?
Yeah, the one story that had the most emotion for it was that Paul went off on a trip to Japan, and he put his view graphs in his checked luggage, and they did not arrive. So, oh my gosh, what do we do now? So he told his story about how he finally got him. It was just within minutes of the talk he was supposed to give. And then, so that I remembered. Never put your view graphs in your checked luggage. Now, we don't even use view graphs anymore, but at any rate, that was then. And another thing that he said that still sticks with me is in your talks, people can't absorb everything you're going to say. So remember the three things you really want people to understand, and make sure they get that part.
Yeah, I think that's fantastic. And actually, I've kind of taken that advice that you just said to heart with my podcast and interviews that I get to do. And I'm so blessed to be able to do, because it's true. People might remember, they say people remember 1 or 2% of a book that they read. We'll talk about The Very First Light, which I remember all of course. But they say you can't really remember it. So part of my selfish motivation in doing these podcasts and conversations on Clubhouse and elsewhere is that I get to remember maybe 3% to 5%, because I have to really read, take notes, prepare. And one thing that really shines through in the reading that I've done with about you and your book, et cetera, is the influence of mentors and the influence of them on your career and even on your style as a scientist. And just now talking about Paul Richards, it reminds me of a story that you told in your Nobel biography about how your father had an influence, and your mother too, on the direction taking you into a scientific career. And you talk about your father who had a laboratory with liquid nitrogen and calorimeters. He was at the University of Wisconsin, I believe it was Madison. Was that right?
Well, that was for his doctorate. But when I was a kid, he was at Rutgers University.
Oh, right. Yeah.
And we were living on a research farm way up in the far north country in New Jersey.
And he became expert in this optimization process to produce more protein, I suppose, and
more and better milk.
Yeah. And that's a vital importance to, it's the number one export of Wisconsin, as we all know, but then of course for the whole country. But I wonder, what was his influence on you as a scientist? It's inescapable for me, just for those that may not know. A lot of what John has done in his world was using types of calorimeters called bolometers that measure ancient heat, not ancient milk protein or new milk protein. But can you tell us about the influence of your father and other scientific mentors that you had, ranging from Paul Richards and Richard?
Well, I'd say the most direct influence people have had on me is similar to what people said about David Wilkinson. He said, people said that he said, get students, give them really hard problems, maybe impossible problems. Don't tell them that they're impossible, and let them figure them out.
Yeah.
And so I have taken on really hard problems, and they've gradually yielded bit by bit, so that we could actually build the COBE satellite and now even the James Webb Space Telescope. So our whole community has been doing this. Bit by bit, we've been inching forward to make better equipment, to make measurements that would have been completely imaginary when I was a youngster. Nobody could have ever dreamed you could measure that.
Yeah, the precision, the phenomenal precision. Of course, John, you're most famous in this iconic image that I think about almost every day when you displayed those view graphs back then, or what have you, with showing the black body spectrum of the cosmic microwave background with these tiny little boxes. I'm like, why did he take off the boxes? I was just a kid back then, but it was, in reality, it was the error bars, the expression of the uncertainty that we all have to account for as scientists, because we can never do a perfect measurement. But in some sense, this measurement, or maybe the cosmos in a sense, because those error bars, you had to magnify them 400 times just to get them to be visible on a view graph. But I wonder, when I saw that, I remember hearing that it was the most perfect black body that was imaginable. And I remember thinking, well, how do they know that it's the most perfect black body? How do you compare to a standard black body to say, I've done better than a black body? Maybe you can recapitulate, John. It'll be a delight for me to hear. What is a black body? And how do you know that that was the best black body ever measured if it's the best black body ever measured?
Yeah. So, okay, just one small factual modification. The first graph that we showed had a precision of maybe 1%. It took quite a long time for Dale Fixon, my colleague, to run the software that would get rid of every error that we could get rid of. And so that's what it took to get 50 parts per million. So that was a huge accomplishment on his part. So what about the design that made this possible? Well, number one, it's a differential instrument. So we say, okay, we'll have a black body and we'll put it in and out of the antenna and see if anything changes. How different is the sky from the ideal thing that we flew? And so then you have to design that black body so it's really black. And then you have to argue that it is not reflecting anything else but itself. And so we designed with that in mind, and we tried to test for it. So we believed that it was, and we argued that it was. So you actually need to measure the reflectance of this thing. The reflectance is 1 minus the emissivity. So we measured, and David Wilkinson did it in a lab, actually. It's about a part in a million. So that's astonishing. You can do that if you have complete control of the shape and the temperature and the environment.
And so those controls allowed humans really to establish that the microwaves that we were perceiving in all directions were indeed of a thermal character. And I had on recently, John, I had on Jayant Narlikar, who I've known personally for 20 years almost. And he used to visit my colleague, my late great colleague, Jeffrey Burbidge, who is here at UC San Diego, who worked alongside Jayant with Fred Hoyle in the maintenance of the view, even after COBE, FIRE-S, and DMR. He maintained the modified version of a steady state theory, which came to be called the quasi-steady state universe. I wonder, what did you make of all that after not only making this discovery, but even going on, as you say, onto even bigger, better, or not bigger or better, but just different projects that being so settled in your mind that it was a black body? I mean, Fred was no dummy. He was a brilliant man. So is Jayant. They still believe in the, Jayant does. Unfortunately, Fred and Jeff are no longer with us. But Jayant still believes in a version of the steady state model being competitive or at least believable, plausible in some sense. What do you say to people like that are so bright, but have this view that certainly is heterodoxical?
Well, I usually don't think it's worth arguing because people that have made up their mind have their own reasons. It would be interesting to ask, well, why do you still believe this when we have this other evidence? But I have not made that question. So looking at it from the outside, we say, well, how can you possibly imagine that your story produces this degree of perfection of the spectrum? And so, as far as I know, they can't do it. But I guess they think they can.
Well, yeah, they were very creative in terms of evading the different constraints, even after Penzias and Wilson, and even after the discoveries that you and Paul made early, even before COBE, and David Wilkinson, who is my grant advisor, my PhD advisor's advisor, a titan of cosmology and astronomy, for whom the WMAP satellite gets its W, and rightfully so. But they would come up with all sorts of other ideas, like there was thermalization, there was dust, and unfortunately, I happen to know a lot about dust, as you know, from it playing a big role in the lack of a Nobel Prize, perhaps for at least maybe not me, but for other people on my team, and if not me. But but this thermalization of by dust and this creation field that they claim, and it's a cute thing, but they claim that this creation field, which is what made the quasi-steady state created a certain amount of molecules of hydrogen every year, and that is actually one of the underpinnings that was backed up by the discovery of dark energy. So not only can they explain the CMB and its black body character, but also the accelerated expansion of the universe. So now I'm not agreeing with it. I'm just pointing out sociologically, it's very hard for what they say an ugly fact to kill a beautiful theory. Even in Dickey, Peebles, Roll, and Wilkinson, that model that they talk about, and you know this extremely well, is right before you were in school. But they never mention the Big Bang once in the companion paper to Penzias and Wilson. They talk about a cyclic universe or the collapse of a previous cycle or something like that. So it's interesting. What do you think it would take for? I mean, do you think we can ever have unanimity in science? Do you think that's a good thing or a bad thing that we, to achieve unity? But maybe we can't have it.
Well, I don't know that it's an objective that we should seek. And I think nothing would make people happier than to discover that we've all been wrong about something. And we've all got something to do, and we've made an advance of some sort. So I don't think we're stuck in some kind of groupthink the way some of my other colleagues think. I think we are very busy pursuing the possibility that we're all wrong. But each scientist has to make some judgment. Well, where is the payoff likely to be? So if you're looking where it's pretty unlikely that you're going to find a discovery, then, well, after a while, you might get tired.
Mm-hmm. Yeah, I've been doing a few conversations on the podcast with people surrounding theories of everything, and whether or not such a quest is motivated by a desire to seek unification or beauty, symmetry, simplicity. And I'm reminded, as one of your heroes, Richard Feynman, used to say, science is the belief in the ignorance of experts, meaning that if Einstein just trusted Newton, we would never have heard of general relativity. And it's a good thing to be suspicious. I don't know of a scientist that says, oh, well, Fred Hoyle said it. He's an eminent scientist. He discovered the Hoyle resonance and stellar nucleosynthesis. So I'm just going to believe him about the steady state.
No, that's not us. We don't do that. But the general public might think that we're all group thinkers because we all say the same thing, but that's because the evidence is pretty strong.
That's
usually.
Right. Yes, and I think there is this notion in the context of perception by the public of science as kind of this all powerful thing. As I might have mentioned, we have this Arthur C. Clarke Center for Human Imagination at UC San Diego, and this podcast is part of that center. I'm the co-director of it. And Arthur C. Clarke used to say famously, we open the podcast every episode. This one will have it too. And we open it with his words saying, any sufficiently advanced technology is indistinguishable from magic. And I love that quote, but it also connotes that, we're doing magic. And you don't ask a magician how he or she does his or her tricks, right? You just trust that they know what they're doing. But it's interesting to see. I always wondered, because, you have, so we know in hindsight that these discoveries borne out, but there's, I get emails every day, Mather was wrong, the Big Bang never happened. How do you, because I see you as this happy, very slender and fit Buddha, that nothing, you're kind of impervious to attacks and assaults, and you have this just gravitas, and you've always had, I think when you were a baby, you had gravitas. I don't know, correct me if I'm wrong. But
I don't remember, didn't take notes.
We'll ask the historians out there to do some research. But John, how do you weather the attacks? Because until something is confirmed in science and consensus can be built up, it's an anxious thing, right? I mean, I heard from Barry Barish and Ray Weiss that they were kind of nervous after the initial discovery of the in-spiral of these black holes, until there was a second event on Boxing Day in December of 2015. And then they were like, forget it. It was slam dunk. And then they decided, let's go full ahead. How did you handle it's hard, as you said, to go into space. So how did you view it? I mean, did you view it something that we needed to confirm? I recall DMR was only the differential microwave radiometer. If it had been a factor of 2 less sensitive, maybe it wouldn't have been a discovery. So how do you handle the attacks as a scientist in a way that my audience can kind of learn from how to stand true to what you believe?
Okay, well, lots of different jobs in science. My job, as I looked at it, was build some equipment and go measure something. And the interpretation is some other person's job. So when I say this is what we found, I think it's right. We've done the best we can. We've got a big team of scientists. We all looked backwards and forwards all over everything. We couldn't find anything wrong that we did, and we haven't thought of anything wrong that anybody else did, and we haven't even thought of a way that the universe could fool us. So this is the best we can do. Here it is. So that's our job. And then plenty of other people say, well, no, that can't be right. So a little story there. When we showed our spectrum at the Astronomical Society and we got the standing ovation, somebody heard Jeff Burbidge, who was chairing the session, to say, they've swallowed it, hook, line, and sinker. So, okay, so people certainly have strong opinions about the interpretation. But there was no question in our minds that we had confirmed that black body curve. We were a lot more cautious about the hot and cold spots because we knew how hard that was, and there were lots of ways that we could be making mistakes, or that the instrument could be fooling us, or that the nearby universe could be fooling us. Dust clouds, just as you said, they could all be in our way. And magnetic fields around the Earth were bothering the equipment. So we had to fool with all of that stuff and try to imagine how we could be fooled. And so it was about 6 or 8 months between the day when Ned Wright showed the science team that here are the spots, and the time that we agreed that it was ready to show the world. So, by the way, Ned was the person who knew the first. He was the very first one to know.
Yes. I gave a talk at UCLA a year or two ago and reconnected with Ned. Ned was actually the editor for my first AppJ article in the late 90s as a first author. And he sent back the first draft. This is, on Pine, Emacs or whatever. And he sent back like, I don't do MIME. Okay, I don't know what that means, but I guess I attached, some file as an attachment. This is pre-PDF, basically. He's very terse, as they used to say about your fellow Nobel laureate Dirac. He never uses 2 words when none will do. But Ned is a phenomenal influence on many of us in this field. And you point out in your book and elsewhere, you say COBE was a team effort. Our team gave their complete concentration and support for a very long time. They dealt with having to redesign the mission after the Challenger explosion. They tested the observatory extensively, and they fixed the problems that they found. The analysis team found ways to compensate for systematic errors that were built into the designs, and in the end got the measurements far beyond the formal requirements for sensitivity and accuracy. This, to me, brings up 2 points. One is the importance of a team and leadership in science, and the other one is dealing with setbacks, such as the things that are out of your control, the Challenger explosion, a COVID pandemic. Let's talk about that. First of all, team. How do you hire people as a scientist lead scientist on JWST? How do you think about it as a team first and foremost? After all, maybe I'm wrong, but I never got any, I know I'm not wrong about myself, but I never got any training on how to manage a team. Did you get some special training on how to manage and build a team and inculcate the values that your team has? Or how can we learn from you these practices?
Well, I wish I could tell you. When I got to Goddard Space Flight Center here in Greenbelt, I was only 30 years old. I said, I do not know how to do any of this. I'm going to go to my meetings with my fellow scientists and engineers, and we'll work together on this. But I'm not the person to manage this project. Don't even ask me. I have no idea how to do that. So Goddard assigned professionals, professional scientists, professional engineers who are my supervisors and my mentors. And the engineers really did the hard job of figuring out how to make this thing work. They far outnumbered the scientists. And so we were able to join an existing engineering organization that already had basically all the talent that was needed. When I came to Goddard, there was a project we were just finishing up called the IUE, the International Ultraviolet Explorer. And it was launched soon after I got there. And so the team still was intact. So, okay, let them take over this new idea. And let them figure out how to build something that will do what those scientists want to do. And they were brilliant. Very wonderful people. I still am in touch with a few of the originals. And so basically, they knew how to do the stuff that people think I did.
And then, yeah, sharing the credit, and then making the team resilient enough to overcome obstacles that are out of your control. After the Challenger blew up, I mean, that's one of my earliest memories as a kid in ninth grade, being brought to some auditorium and seeing about to watch the launch of this teacher going into space, and then the tragic, awful images that resulted from that. But and you were at NASA, and so how do you overcome those kinds of challenges that none of us can put? We all make these risk registers, that document, well, this is a probability of the euro is going to fluctuate against the dollar, and then in Chile is going to have a peso, and then that's going to cause concrete locally. Anyway, we have all these matrices, and we have to, but they never have in them, explosion of a vehicle, or I mean, maybe in NASA they do, but not in what we do. And yeah, so how do you deal with those really unknown unknowns, as a fellow Washingtonian used to say?
I don't think there's a big plan. You deal with them when they arrive. So we were very fortunate. Some of our managers said, we'll find a way. They didn't know what it was going to be, but we'll find a way. We didn't get this far to give up. That's how everybody felt. So there were a few people who said, well, actually, the shuttle that we were going to launch the COBE on just wasn't really that good in the first place. So let's get a different rocket, find a Delta rocket or something. So our deputy project manager said, I'll find one. And he did. It was quite a significant accomplishment to find one when they weren't available. But he found one. And so, as it turned out, it had to be assembled from parts that had been lying around, because there was not actually a whole rocket available. But people knew that the project we were building was important enough to be worth trying to rescue. And it wouldn't take too long before people realized, actually, if we could solve this problem, the COBE satellite could be the first thing that we launched for science after the Challenger.
Right.
And it was. So even before the space shuttle took the Hubble telescope into space. So we went from being, well, okay, do it if you can here. This is a sort of best efforts project. We know this is really hard, to suddenly you're the one, you have to get this right now. So hurry. And so that actually cleared a lot of obstacles. And basically, you don't have to argue with people to tell someone something's important when everybody can see it and feel it. So everyone knew. Actually, although I didn't quite believe it, people started saying right at the beginning, there's a Nobel Prize in here. And I thought, well, there is or there isn't. It's not us to say. We have to do a good job.
That's right.
So, well, we try to do a good job. So I think that that feeling went all the way from the working level all the way up through top management at headquarters. And I suppose maybe even in Congress, some people knew that was important.
And when I look at NASA today, I see that it has a very strong brand. It's not to say that it hasn't failed. I had on astronaut Scott Parazynski. Just a reminder, people listening on Clubhouse, we have many of you in the chat room. Hopefully we'll take some questions for Dr. Mather in just a bit. But I produce videos with, as I say, billionaires and brainiacs and everyone in between, which includes me, because I'm neither a billionaire nor a brainiac. But I had on astronaut Scott Parazynski, who is an amazing individual. He's spacewalked 7 times, 5 times on the shuttle, attempted to reach Mount Everest once, and failed miserably. And then he came back and did it again. And he and I were talking, and I talked with Jessica Meir, who is an alumna of UC San Diego Scripps Institution of Oceanography. I talked to her while she was on the space station, which I pointed out was only 200 miles away. It's not that big a deal. But and I've talked to 2 other astronauts. And I always say NASA's got probably the strongest brand in the world. I have clothes that say NASA. My kids have clothes that say NASA on it. How does it feel to work in an organization like NASA for basically your whole adult life?
Oh, well, to me, it's just going to work and work on the coolest thing there is to work on. So we don't usually think about how special that is. We
Mm,
just, have our job to do. We got to make this thing work.
that's
Whatever it is that we're working on this week, we got to make it work because, we're part of a team. And if it doesn't work, all kinds of bad things can happen. Not only won't you get the answer that you wanted, but your whole team will be embarrassed. Your support from Congress and so forth might dry up. You might just end up wrecking things badly. So we all take it very, very seriously. And so nobody wants to be that person who dropped the ball.
right.
The people that I work with are extraordinary about keeping track, not letting anything get away from us.
Talk about now your desires and your exposure to teaching, to communicating discoveries, not just by yourself, but you're always so gracious and generous to make sure that you always tell it's science is a team effort. Talk about your book, The Very First Light, which changed the way I thought about my career when it first came out, and wanting to kind of channel some of this infectious passion and curiosity that you have, but also being cognizant of the politics and sometimes competition.
Mhm.
And no Nobel Prize winner except for one, and I'll ask you this later when I ask the question I ask all the Nobel laureates who honor me by coming on my show about the imposter syndrome. We'll get to that later. But basically all of them said, like, you got to be crazy. Like, no one ever thinks about winning a Nobel Prize. But a lot of other scientists do think about winning a Nobel Prize. I talk about in my book, Losing the Nobel Prize. When I came here, I was told by the chairman, who was the son of Nikolai Basov, who discovered the laser, along with your former professor, Charlie Towns. And this discovery, he basically told me when I was hired, well, you're working in a field and we expect you to win a Nobel Prize, basically. And this is a man whose father won the Nobel Prize. Talk about how when you do your writing and outreach to the public, how do you kind of balance this thought in the popular imagination that science is about credit, is about egos, tense politics, as well as the cutting edge science and engineering that we have to do? How do you balance that, and why is it important to communicate that to the public?
Oh, my goodness. Well, it's a large and difficult subject. My perspective is we're in this together, even if we're competitors. If you're working on a project and I'm working on a project that's supposed to measure the same thing, and we don't get the same answer, that's really important.
Mm-hmm.
So our job is to get evidence, not to win. So if we can get evidence, then that's a win. So and we don't know what the evidence is.
Right.
So I think a good scientist is always saying, I'm going to get more evidence. I'm not trying to browbeat anybody into believing me. I'm just going to get more evidence. And so if you're in my world where the job is to go measure things, then we're always thinking how to make a better instrument that can measure better. So that's always in the back of my mind. How can we measure something better?
Mm.
And then, of course, if you have an idea, then your job next is to say, persuade someone to support you so you can do this. So then you have to sort of spin a story about what you could discover if you could build it.
Mm-hmm.
So then you always have to remember, well, it may not be that way. So I never worried very much about credit. I thought, to tell the truth, the only way to get credit is to give credit.
Mm.
If you think you can capture credit by claiming you did something, well, that'll last for a week. And afterwards, people will remember you that you're the one who took their credit away from them. And that's not a good thing to do. So the truth is we're all in this together, even if it doesn't feel like it.
That's a beautiful way to say it, John. Talk just the last bit about competition, maybe the public. I've noticed a proliferation, and you were a part of it. I was tangentially a part of it, in a relatively new phenomenon, which is the explication of scientific findings to the public via press conference, and the various ways that takes place. Recently, we've heard many big discoveries, ranging from possible evidence for life or byproducts of life on the planet Venus. We've heard, tales of extraterrestrial technology, potentially visiting the Earth. We've heard, obviously, the discoveries of my experiment, Bicep 2. et cetera, where these were held press conferences, and it's true that these discoveries, if confirmed, are quite amazing and astounding. But the question of the obligation of scientists to not only have publicize the results because taxpayers pay our salaries, but also to correct any misapprehensions that what we claimed once on the front page of the New York Times, maybe that didn't turn out to be so. So I wonder, with your experience, your long career, what do you think about press conferences, and are they a net benefit for science or not?
Good question. Depends on motivation, doesn't it, a little bit? If your motivation giving a press conference is to explain something that you're very sure of, that people will want to know, that's one thing. If your motivation is to be first and to claim credit, then you're often pretty likely to be in trouble because it's not mature. So standard policy for me and most of the people that I work with is no press conferences until your manuscript is selected for publication. So we just don't want to get into trouble, and people do. It's so easy to be eager to tell the people and to say how cool this thing is, and it's also so easy to be wrong. It happens so often, and who knows whether your current excitement is right or wrong.
Yeah, when I think about these press conferences, sometimes I say, we should have we don't have a very big PR budget as it is, but maybe we should keep half of it in reserve to hedge against the fact that we may need to have a if not a retraction, an explanation or an update to the claims that were made. So we have some questions on Clubhouse. I'm going to take one or two right now. So these are listeners, John, that tune into the show. I'm going to take Harveen first. Harveen, welcome. You're talking with none other than John Mather, who is a titan of the field of astronomy, cosmology, and other experimental astrophysical endeavors. Harveen, go ahead. I'll see if make sure John can hear you. Hello.
Hello. Thank you so much. Dr. Mather, my question really related to the funding of science, because in your career, through the span of your career, it's covered the period from just a few years after the moon landing all the way to these years where it seems that it's so difficult to get consensus on facts and science. How do you think we can continue to shape a consensus that it's important for governments to allocate budget to science, especially when there seem to be so many other competing priorities?
I like people to know that there are practical benefits for the science that we do, along with the intellectual and emotional benefits that we get. So I like to share both. So in my quest to understand the early universe, my basic wish is, how did I get here? I want to know, what are all the steps from the Big Bang till now, as near as you can tell. So there are an awful lot of them. And so a lot of the most complicated ones are biology and geology. So I can't work on them. I don't know anything about them, but I can cheer when those people do. Then it turns out, of course, those are really practically important for our own future, since we're busy changing the planet that we live on as fast as we can go. So there's a huge practical importance of basic science. Bill Gates is now telling everybody, as he's been saying for quite a long time, if you don't figure out energy supply and get to zero carbon, we're cooked. That wasn't his word, but we're cooked. So we can't get there with just be more economical about your food and your driving. You have to actually solve a big engineering problem. And right now it's not solved. So from a very practical sense, we have to work on that. If we want to be here in 1,000 years, we got to solve that one. And the only path that he shows us is science and engineering. You can't really expect the public to do what it takes unless somebody's given them the tools. I can't buy an electric car if there is none.
Very good. Okay, Another question. Let's go to Eric, and then we'll go to Arthur, and then we'll continue with some questions I have. So, Eric, you are now a speaker. What do you have to say to Dr. John Mather?
Hi, Doctor. I had a question for you from the perspective of, like, I'm a entrepreneur working in biotech, and I was curious if you could comment on how funding has changed over the course of your career when dealing with private company partnerships with government, so universities finding industry partners, and how that kind of perhaps has changed, or where you see that there's problems or areas that we could address. So I have a vested interest in that, and I'm also curious to see effective strategies. There's been a lot of demand for coronavirus research, and everyone pushed for it, but now people are kind of becoming complacent. So.
Okay, well, I don't actually have information to properly answer your question. I would say over my lifetime, there have been huge changes, though. When I was young, for instance, the military supported basic science. And then Congress said, no, we don't want you to do that anymore. That should be handled by civilians. So that's a big change. So I think you have better information than I do about your question.
Okay, fair enough.
Thank you.
Thank you. Arthur, she is the next one with his hand raised. Arthur, you're on with Dr. John Mather.
You mentioned earlier that if Einstein never doubted Newton, he would never have developed his equations of relativity and all that. I'm curious what your opinion is of the current education system, where there is only one right answer, and what your ideal education system would be.
To answer anything about the current education system, I would have to imagine it. And I have not been a student for these many years. So honestly, I can't tell you. So I can tell you, though, that I'm astonished at how bright the young people are that are coming into our labs. There is no question in my mind that they're smarter than I am, and they're quicker than I am, and they know stuff I could never know, and they are masters of tools that I don't know. So at least in the sciences, we are doing a brilliant job. I certainly, however, read the news, and I find out that most people do not receive the civics education that I got beginning in 4th grade. So most people are not shown how the government works. So if they don't know how it works, they try all kinds of weird things.
Yeah, that is a danger. So let me turn now to your next project, which is JWST, and this is a very interesting project for many reasons. One of which is that it may, reveal some of the most interesting and curious aspects of the universe, as well as aspects of cosmology. So, can you talk about your role in JWST, and then what its status is? If that's not too controversial, we talked about civics for a second, so yeah. It could be controversial to talk about its status. But please, what is the mission of JWST, and where does it stand currently?
Okay, well, JWST is the James Webb Space Telescope. The James Webb was the second administrator of NASA. He's the man who went up to John Kennedy and said, here's the plan for Apollo. And then he made it happen. So about 8 years after he said, here's the plan, we actually landed on the moon. So that, to me, is a miracle. He knew what he was up to, and he knew how hard the job was. So this is a reminder, by the way, to anyone who's planning a great leap forward. Don't believe everything people tell you about how much it's going to cost. There's a story that he realized he didn't know, and he doubled the budget in the taxi cab on the way to see the president, and then it was enough. But if he had not done that, it would have been a major national embarrassment. So just remember that scientists and engineers are optimists. And no matter how hard we try, we cannot think of all the bad things that are going to happen to us. And that's probably good, or we would not maybe even start. So anyway, that's who James Webb was. The telescope is a successor for Hubble. It is much bigger and much more powerful. The mirror is 6.5 meters across as compared to 2.4 for Hubble. And the telescope is cooled down to a low temperature so that it can pick up infrared light. So you and I are transmitting 100 watts or maybe more, several hundred watts of infrared power. And so if the telescope is warm, it can't see infrared. So we have made a design which is bigger and more powerful and cold, which implies all kinds of terrible engineering difficulties, but they're mostly solved. So the status is, as far as we know, it has been through its final vibration test at the company that's putting it together for the final steps in California. That's Northrop Grumman Space Systems. We are about to button it up and say it's ready to go in the box. So that'll take about 6 months, but because we have to be very carefully going through every single detail. So it's coming. And as far as we know, it will meet all of its requirements. Nothing has gone wrong about does it work the way we think. So I'm feeling very fortunate about that because stuff happens and we've escaped all the major hazards, sometimes after a huge effort, but we've managed to deal with them all. So if we are fortunate, we'll be shipping the telescope to the launch site in French Guiana in August sometime, and then launching it in the end of October. So coming soon. It's not so far off now.
No. And can you tell us about the mission of it? Is it just a super Hubble telescope? It sounds like it's going to be very different from the Hubble telescope.
It's super and it's different. So, for instance, this picture that I'm showing you behind my head here is a picture taken with the Hubble. And it shows that if you point your telescope at a more or less empty place in the sky, it will be filled with galaxies. When people took that picture, they were astonished to see how many galaxies there are there, and to see that even the Hubble was not going to be able to see far enough to answer our big question. The big question was, well, how did the galaxies get formed, and when? And the upshot was the Hubble telescope was not powerful enough to answer that question. So they said, build us another one that can see longer wavelengths so that we can see the redshifted distant galaxies and is bigger and more sensitive. And so that tells us to build this terribly difficult telescope we are putting up. It has several other things to do. We are going to look for how do the black holes form and grow. Every galaxy there seems to have a black hole in the middle. How did that happen? When did that happen? We're going to be looking at stars being formed inside their dust clouds close up. Here, right nearby, even in the Orion Nebula, for instance, the beautiful dusty glowing clouds of gas are forming stars as we speak. And darn me, you can't see inside. The interesting stuff is happening where you cannot see it because dust is opaque. But as it happens, nature says, well, if you use a longer wavelength, you can see through the dust. So the Webb telescope has the longer wavelengths that we can see inside those dust clouds to see stars being born. So that's another piece of our history that we want to know about. Then the thing we didn't know we would be able to tackle would be, how about all those planets? We know now that most stars have planets and most stars have little ones at about the right temperature to be like Earth. So let's go look. So I think we're going to get some surprises. And I don't know what they are. If I knew that, I would be trying to plan to make an observatory program to get them. But I think somebody's going to find something very surprising.
Yes, every time we open a window, and especially one from such a high perch, the highest frontier, we are almost guaranteed, all but guaranteed, of extremely interesting, but also maybe serendipitous results that we didn't expect. It's kind of interesting thinking, going back to COBE as we close out. You know, people suspected the CMB was a black body, but there were alternatives. And as I mentioned earlier, there were alternatives that persisted even, here in San Diego for many decades, even after, or decades after the discovery of the CMB, but even a decade or two after the discovery made by COBE and VIRAS and DMR. But, thinking back, how tenuous things are when you set out to do something, and all the pitfalls and all the challenges that can come about along the way. And I wonder, at certain times, maybe this is the right time to ask you the question I've asked the other 8 Nobel laureates who've come on the show about half theorists, half experiments / observers. And I want to ask you this question that comes up a lot in academia. We're always judged, we're always graded, in undergraduate, even in graduate school. Then you have to get a prestigious postdoc. then you have to fight it out really to get one of the few faculty positions in this field. I mean, there are more people that have won the Nobel Prize or let me say, there are more people on the space station right now that have won the Nobel Prize in cosmology and physics that are alive today, shall we say, including you, thankfully. And the question I have for you is, do you ever, along the way, do you ever deal with the imposter syndrome? Do you ever feel like, or did you ever feel like, rather, you weren't, good enough to do whatever it is that you were being commissioned to do? Did you ever wrestle with that effect that academics face called the imposter syndrome?
Well, I've never actually called it the imposter syndrome, but I think the life of a scientist is similar to my life, which is every day I get up and work on something which I can't figure out yet. So every day I'm the imposter who doesn't know the answer. And so now what am I going to do? I don't have any choice. This is my job. I'm going to have to work on the thing that I haven't figured out yet. And so once in a while I say, well, there's somebody over there that's really smart. What do I do? Ask that person for help is usually the best plan. Don't try to beat them, try to join them. So it took all of the members of our COBE science team to do what we did. And it takes all of the members of our gigantic engineering and technical science team for the Webb telescope. Right. There are thousands of us. And the telescope could not go if we didn't have them.
That's right. Absolutely. It's a team effort. I always say science is an infinite game, and it's not like a zero-sum game. It's not like chess where there's winners and losers. We can all win in an infinite game. The problem is nature has an infinite array of armed forces against us, and she wages very cunningly and craftingly against us. It's funny because, people have told me, like Barry Barish, when I asked him that question, did you ever have the imposter syndrome? He goes, what are you talking about? I still have it. I said, what do you mean? And he said, well, when I went up to get my Nobel Prize in Stockholm after getting the medal, and they make you sign this book, you can confirm this, and it has like all the laureates' names in it throughout history, at least, for the last 100 years. And he said he saw Einstein's name and his signature, and Feynman's name and his signature, and Dirac and Salam and whoever else, and Curie and Maria Mayer. He said, I'm not worthy. And he said he still felt that. And I said, if he can feel it, so can I.
Yeah, well, I feel that too. I did feel that when I visited and looked at the list. My name is on that same list with those guys.
Yeah.
Well, they were geniuses. They were brilliant. How did they ever do those things that they did? And I don't know how they did, but they did them. Yeah. So they had the ability, all of those people, to look at nature in a sort of perpendicular way, which was so different from anybody else's point of view. Say, thinking about Dirac and his wave equation for electrons. Whoever would have dreamed outside of him that you needed to write little matrices that don't commute with each other. So, oh my gosh, how did you think of that one? And how did he trust it enough to find a solution that said there should be positrons? Oh man. So there's a lot of incredible imagination out there, and a lot of it turns out to be wrong, but that's why we have lots of people.
That's right. Yeah, and the diversity of viewpoints and vantage points contributes to a healthy, vibrant field that I think is the healthiest field of endeavor of human beings. I'm not saying it's the best. I'm just saying you get to work with people. I work with people from Antarctica to northern Sweden and from Saudi Arabia to California. It's the most thrilling thing to get their viewpoints and talking to people, especially on this app called Clubhouse. What's interesting is that people can be listening all around the world, all over the planet, of every religious faith, of every gender, everything. And just hearing from them and hearing the one thing that unites us all is that we aren't artificial intelligent robots, that have no emotions. We're human beings. And science is a human endeavor, despite the stereotypes to the contrary that we're all just robots and so forth. And John, I want to thank you so much. We don't know each other really well, but you should know you've been a huge influence on my career. I don't blame you for any of my mistakes, by the way, and nobody should. But John has been really a remote mentor to me, and now with the benefit of technology such as this, we can sort of be close together. I hope I can see you again soon when things are well in the world. I wish you all the best. I know you're super busy. Thank you for being so gracious with your time. Have a great rest of your day, John.
Thank you, Brian. It's been a pleasure talking with you and your listeners.
Any sufficiently advanced technology is indistinguishable from magic.